Hello, good morning. My name is Henrique Fernandes, and on behalf of my co-authors, I'm going to present to you the work Infrared Thermography for Impact Damage Analysis on Curved CFRP Laminates used in geostationary satellites. This work was done in a collaboration between Federal University of Berlândia and University of São Paulo from Brazil, together with the Fraunhofer Institute for Non-Destructive Testing and the Saarland University in Germany. The presentation today includes an introduction, presentation of materials and methods, followed by results and discussion, and concluding with our final remarks. First, introduction. Composite materials has been used in several industries throughout the years. The aircraft industry, for example, uses it in the manufacture and construction of airplanes. The Airbus A380, for example, uses a considerable amount in its parts. Here I emphasize a part in the wing which has a complex shape structure, and in cruising altitudes operates under very low temperature, typically -6 degrees, and is subject to impact events that lead to the so-called barely visible impact damages, which cause significant degradation of the mechanical properties of the aeronautic structure that's made of composite laminates, compromising the airworthiness of the vehicle, despite only the small indication of on the external surface of the component. In the aerospace industry, the use of composite materials is also present. For example, the soil moisture active-passive satellite was put in orbit by NASA in 2015. It is in the altitude of 685 kilometers and has a weight of almost 1,000 kilos, 944 kilos, and it's in the so-called low Earth orbit. The satellite, the SMAP, has employs a gigantic rotating reflective parabolic antenna whose structural mesh is manufactured by thermoplastic polymers such as PPS, PEEK, and PEI. Here I show you this parabolic rotating reflective antenna. In the low Earth orbit, the temperature which these components are working is in the cryogenic levels, minus 150 degrees Celsius. And there is also the possibility of micrometeoroids that travels in a velocity of 10 kilometers per second. So if this micrometeoroids hits the component structure, it would cause some damage, especially traveling in such high velocities. So here again we have a complex shaped composite that is subject to barely impact visible damages. So another thing that should be considered. Finally, another structure that is operating in the low Earth orbit is the International Space Station. It's operating in the altitude of 340-350 kilometers, and its temperature changes in the range of plus 121 degrees Celsius, the sunny side, and minus 157 degrees Celsius on the dark side. So we have a structure here that employs composite laminates, and it's subject to variation of temperature, and also as the satellite also subject to impact damage caused by micrometeoroids traveling in high speed. So it's important to have techniques that assess and ensure the safeness of these components that operate in such harsh conditions. In this sense, the objective of our work is to assess the damage on curved CFRP previously submitted to thermal shock cycles and low energy impact, ballistic impact. These conditions were prepared in order to mimic those found in low Earth orbit, like the conditions I just presented you in the SMAP satellite and the ES. In this work, we are going to employ two non-destructive testing techniques, infrared thermography and ultrasonic inspections, because we must of the component is at high levels after the inspection. So our inspection must not impair the component. So we're applying infrared thermography and ultrasonic inspections. Materials and methods. So our specimens were 809 laminate coupons manufactured with PPSC. They were curved at room temperature to make a complex shape part. They were subject to rapid and large temperature range thermal cycles. They were put in boiling water, 100 degrees Celsius. They were kept there for 3 minutes, and then they were transferred immediately to liquid nitrogen, minus 196 degrees Celsius. So to mimic the condition experienced in the low Earth orbit. And then, after the thermal shock cycles, they were transversely impacted with an air-driven rifle caliber 5.5 millimeters with a weight of 1.6 grams, traveling at a speed of 250 meters per second in ambient temperature. The estimated energy of the impact was 50 joules, which approaches well the typical energy to simulate micrometeoroid collisions. Here is a schematic of the transverse impact. So we had 80 samples that which we had 4 different thermal shock cycle conditions: 0, 150, 300, and 500. And here on the right we have an example of the specimen number 15, which was not subject to thermal shock cycles nor impact. So the first technique that we employed was infrared thermography. Infrared thermography relies on the principle that the heat travels freely inside an object through conduction, and when it encounters a defect, a damage, a barrier, it will travel differently. It will have slowly differ from a place without a defect. So we can use, for example, here we have a post thermography heating up a specimen while an infrared camera captures the images. So we can see if there is something inside the component by analyzing the thermograms, the temperature profiles on the surface of the specimen. It has been used for composites for a long time now, this technique. Here we have the setup used in the laboratory. We have the camera, the flash lamp, which was a round flash lamp, and the specimen around 30 centimeters apart from the camera, in front of the camera. Our ultrasonic inspection used a 5 megahertz transducer, and we focus our inspection on the top of the curvature of the specimen. Here we have a short video of one of the inspections. Now our results. Infrared thermography signals are very subtle. Thus, one must apply signal processing enhanced techniques in order to have a better defect visualization. Here in our work, we apply principal component tomography, a well-known method that has been used for more than 15 years now, which relies on signal value decomposition in order to sort components, putting the most valuable and relevant information in the first components of the result. Thus, we can reduce the amount of data from 1,000 thermograms, for example, for 10 components that are really relevant. Here in our work, we inspect the specimens with infrared thermography in the pulse thermography reflection mode setup, and then we applied PCT in order to improve the quality and the visualization of the results. Here we show second and third components from all the specimens. We are showing here the best component, which brings more details. Here in the first row we have the 150 thermal cycle, second the 300, the 500 and the 0. We can observe here clearly in all images that the impact damage that's also visible with the naked eye is here in the center of the specimen, indicated by the yellow arrow. We can also see, especially in the specimens with the higher number of thermal shock cycles, that the lamination around the impact has been formed. So there could be interply and interply T-bonding here. And also we can see cracks in the specimens. We can also see cracks here in the specimen which was submitted to 500 thermal shock cycles but not impacted. Why is that? Because of the stress that this specimen was subject to due to the 500 thermal shock cycles, which could introduce some damage in the fiber and the matrix, causing some cracks. So because the sample, the specimen, was curved in tension, it had some tension on that, the thermal shock cycles cause some of this tension to be liberated and causing some cracks on it, and you can see that here, then indicated by the red arrows. The ultrasound inspection here show some B images. We show some B images here of the samples, the specimens that were not impacted. We have the 150, 300, 500 and 0. We can observe here the specimens that were not impacted, that no visible damage is present. But for the specimens that were impacted, the damage is clearly, and we have more damage when we have more thermal shock cycles. Here in this A here is a specimen that was not subject to thermal shock cycles, 0 thermal shock cycles, and when it was impacted, it created a sharp edge here. So because of that, as you remember, the ultrasonic inspection, the transducer is moved with a robotic arm, and there was no contact around the edges. So that's why we have these very pronounced red areas here. It's not meaning that there is defect there. In conclusion, in this work, specimens prepared to mimic conditions found in low Earth orbit satellites were inspected by infrared thermography and ultrasound. Specimens were curved and submitted to shock cycles, and then they were inspected using infrared thermography and ultrasonic inspection. Results from both NDT techniques show that specimens with higher number of thermal shock cycles had more damage after the impact. Future work of this study includes the use of other NDT techniques such as X-ray CT scan and eddy currents, and also to inspect bigger and more representative specimens. I want to thanks the Alexander von Humboldt Foundation, CAPS agency, FAPESP agency, and the Fraunhofer ISFP for their financial support provided to the co-authors. If you have any questions, I'm happy to answer them now, or you can contact me using my email. If you want to know more about our work, please check our website where you can find more details. Thank you and have a great day.